with the topic. Actually, this is my strategy, not to finish my presentations all today because I'm not well prepared for tomorrow. So I'm going to move some of my stuff to tomorrow. We are talking about now the value engineering. That means not only looking at the performance, but also looking at the cost and trying to optimize both the performance or balance the performance and the cost, so that typically people believe that when you have, general belief is that if you want to increase the performance of something, you need to increase the cost, or the cost will go up, or the performance and cost are directly related or proportional. So they say that you get what you pay for, which is true. That means if you typically, in normal circumstances, if you want to get higher performance, you need to spend or pay more. But that is the case for normal cases. But if we look at other cases, possible cases, you will see that there's another case where we can do cost-effective design. That means we can reduce the cost while keeping the performance constant. So the performance does not go up, but the cost goes down. So we have a more cost-effective design. The next possibility is that we have same cost but higher performance. So still the cost effectiveness goes up, but we get better value for the same money, or the same resources or same cost. So the first one is normal. Second one is that you reduce or you change one without changing the other, which is better. And then the last one is the best one, which means somehow if we can increase the performance at the same time we reduce the cost, that will be great. And that's what we are looking at, that we do both simultaneously. We increase the performance and we also look at the cost and we try to reduce the cost. And that requires more sophisticated, innovative work, because then we are doing something which is contrary to the common understanding. But to do that, we should first of all look at to see what the cost component is. What is cost? And if you look at the cost, many people sort of focus on a very narrow definition of cost and miss the big picture. The cost of the project may start from the financial cost, loan, interest, planning, design, construction, maintenance, incidental, liquidated, opportunities, so many costs from the client's point of view. And when we are talking about only the rebar optimization, then we are only talking about a very small portion of that overall cost. And it may actually not be a best solution for the overall cost. So when we're talking about cost, we obviously need to look at the overall total cost. So we can say cost is a consumption of resources at a particular time, and sustainability is actually a bigger measure of cost over a longer period of time. So when we look at that, if we can look at the cost in a broader term, then it is more sort of easy for us to try to optimize that cost or to bring maximum value for that cost. There is always this curve that people are looking for. Optimization, optimized cost. That means a point in our cost curve or cost equation which is the least cost. And before that, if you change some parameters, cost will go up. And if you change the parameters beyond that, the cost will again go up. And we're always looking for that optimum lowest value, lowest cost for a particular objective. And this optimization people have been doing a lot of research mathematically, numerically, and it's an elusive term if you try to optimize the cost on a broad number of variables. People have been using genetic algorithm, linear, nonlinear programming. Many tools have been used to trying to optimize cost. But that is only really possible mathematically when we are looking at few parameters and few objective functions. Especially if you look at the optimization, you can see that the optimization can be at many levels. Just broadly speaking, you can say that I would like to optimize this cross section to put the minimum reinforcement or minimum cost of this cross section, or one column, or just all the columns in a floor, or one floor, and so on. So the optimization, as soon as you change from one optimization to another, you will find that one optimal solution no longer remains optimum. For example, let me just try to talk about the column. Theoretically speaking, each column and each floor has a different load or demand. So if you are looking for optimizing column, each column must be different in terms of the size, in terms of the reinforcement, concrete strength, rebar arrangement, and so on. And that is theoretically possible that each column is designed individually, independently, and is individually optimized. However, if you have to construct so many columns with different formwork, different construction, and so on, it won't be optimized over the height of the column or over all the floors. So an optimized solution which works very well at one element or one cross section will no longer be optimum when we try to apply it to a broad range of columns, considering formwork, considering construction time, detailing, inspection, space wastage, and when we bring in other variables, solution that appears to be optimum will no longer be optimum. So it's very important that when we start looking at the cost optimization or cost value, we look at the value in a bigger term, the final outcome or the final output for the client or developer or public, and see what value this decision has for them rather than only looking at reinforcement. I remember one of my friends, he used to be really good at calculations, and I'm talking a long time ago when we used hand calculations. And he would pride himself on saying that I have this beam or a slab which is now least optimum design. I have achieved the minimum reinforcement by curtailment, by changing bar sizes and everything. And he would take 2-3 days to do that. And I would ask him, you have spent more time in optimizing an element where your time input was actually higher than what you saved. So it's no longer optimum to spend resources to optimize something which doesn't ultimately give value to a project in bigger terms. And I think that's what we need to focus on and try to educate our other friends that the cost should be the value and resources on a bigger bracket. And like for example, small changes in something can bring benefit. Reinforcement in a wall. If you distribute the reinforcement, you get a certain performance, which is the let's say moment capacity curve. And if you distribute it differently, you get another capacity curve. Nothing has changed. The reinforcement quantity is the same, only the arrangement has changed a little bit. We need to maybe spend a little bit more time or a little bit different way of calculating, but we can increase the performance for the same reinforcement quantity, or we can reduce the reinforcement for the same performance. So either way it can be done. So this is an example where detailing or technology or attention to these kind of things can actually enhance the performance. This is exactly what we are talking about in terms of performance-based design. That we look at the things and see, okay, do we really need it like this? Does this detailing need to be like this? Can I find a reason for not to do this? And if we can satisfy ourselves that that is okay, then that decision could actually have a big impact on the cost. Because like I said, confinement in a column, if we can prove that we do not need confinement on all the floors and only on certain floors, that cost can be significant. And we can take that and put it where it is needed. We might need to increase shear reinforcement in critical location in shear wall, which we should not compromise. But there's a lot of other locations where performance-based design or the detailed modeling analysis that we have done will give us the data or information to do a better value for the same resources, to get a better performance for the same cost. So demand capacity ratio in all bigger terms, we can always look at them. We can try to see, can we get the optimum design capacity or utilization ratio? Typically, if you can get about 70 demand capacity ratio or utilization ratio, about 70%, that's really, really very good in most of the members. But we can. mostly we get much less, 0.3, 0.4. If you get more than, if the capacity ratio becomes more than 0.7, that means you're too close to the limits. And then some members may be threatened by the exceeding the demand capacity ratios. So we are looking at that optimum level of about 70 overall on the structure. And anything below is going to be not efficient, is not cost effective, it's a waste of resources. Anything above may be too close to the limits. So one way to look at it, whenever we finish our design, we can do some kind of a capacity ratio check or utilization ratio check on members, on different demands, rotation, ductility, whatever performance criteria we set, we check and we see, okay, we are getting about 60 to 70%, which is pretty good. And if not, then we can improve the design. So that's the ideal, and that's not cost effective and not safe. So focus should be maximum value for resources, cost effective, not necessarily low cost. Last item of the previous presentation is on the peer review. Because all of this requires that somebody else is also looking at what we are doing, so that we do not optimize too much, we do not cross the line and make it unacceptable. So peer review would be the next one. Because we have so many people involved in a building project, we have the client, owner, architect, structural engineer, geotech, peer reviews, builder, contractors, lawmakers, building officials, legal and juristic system, and everybody. So we need to make sure that all of these people, their interests are taken into account, and when we are designing, making some decisions, and a third-party reviewer typically should look into those aspects. So peer review or independent review is important. Many building codes, many city codes require this to be done. For example, performance-based design generally requires to be peer reviewed. Similarly, let me just give you an example of New York Building Code. The New York Building Code requires the peer review should be carried out for buildings that fall into this category. Number one, important buildings. Number two, slender buildings. Tall or large buildings. Critical members that have critical members. Or analysis that use nonlinear analysis techniques. So if any of these things are present in the building, then the New York and many cities in the US require that a third-party review be carried out for the design. So you can see that many of the buildings in Bangkok or in Philippines will actually qualify based on this requirement, and the third peer reviewer should be engaged by the clients or the developers to ensure that things are going well. However, the responsibility of the peer review does not shift. The engineer in record still retains the responsibility of the design, because the peer review can only recommend, can review and give comments, does not have the authority to change the design. So the comments by the peer reviewer may or may not be accepted by the client or by the engineer in record, which is fine, but at least they are made and they are evaluated. So reviewing engineer report states his or her opinion about what they find, and that opinion becomes important from the point of view of the designer and also the owner, and they may incorporate some or all of those recommendations. But the responsibility still lies with the engineers. This is the typical scope of work for review. Could be check structural engineering concepts, potential behavior, and value improvement suggestions, constructability requirements, peer review findings and peer review report writing is part of that, and then meetings with the clients and other people, review structural design criteria, that should be the first time, and review all the materials. Basically, the independent reviewers will start from reviewing all the process in the document, and this is very common in many industries, aircraft industry, product industry, mechanical, electrical, electronics. All designs are reviewed carefully by third party because the products will be made in millions. You all know what happened in Galaxy Note 7. I'm sure the review was done, but I don't know what happened. But still, something got through. And look at the damage caused to people and to the reputation. I was actually reading, it was very interesting. They reported that the first time in history, Apple has 105% of the profit of the whole market. How can you have 105% share of the total profit of the market? Because Samsung lost. So their loss is converted to, and Apple only has 13% of the market share, but 105% of the profit share. So you can see that sometimes companies who go into details and you do a lot of things, they actually can make big profit margins. So the last slide on this topic is that if we have peer review, we have the basic design, performance-based design, value engineering, all put together under the supervision of the client, with the public officials giving the approvals and design codes and guidelines as the basis, then we can achieve high performance, high safety, high value, cost effective, and sustainable buildings. Thank you. This is the end of my previous topic. I'm going to start the next topic now, the one that I'm supposed to present now. And I'm going to leave my next topic half, which I will present tomorrow. Yes, I will actually continue with a topic that we also heard in the morning from Dr. Karoon, but my perspective will be slightly different. Dr. Karoon presented to you challenges from real case studies. I am going to take a little bit conceptual view of the challenges from the architects and see what those challenges are presented to structural engineers and what are the solutions. So key challenges, let me start with, we looked at the tall building. So we also looked at the tall, we have low tall, low rise, low tall, tall, very tall, super tall, and mega tall. So all these, they're running out of terms. I don't know what they're going to call when they cross 1,000-meter building. Yeah, I think super mega tall, something. So we already are running out of tall definition because so many tall buildings are being made. And if that is the case, that means challenges are simply increasing. In every time we come up to these new definitions or new buildings. So the height is primary challenge for the structural engineers. And why? What can the height challenge give us? As you can see from here, that the height is not, the tallest building height is increasing rapidly over the last few years. Even though the last part is only a needle, but still the height is increasing. So what challenges does the tallness bring us? First of all is the weight on the vertical elements. Actually, one of my class assignments sometimes is to find the specific length or specific height of a material. You know what is that? Specific length or specific height of a material is that if you just make that material, it will break by itself by its own weight. Elevator people know that very well. They're shaking hands. Yes, we know that. Rope reaches that value probably. So if you just take steel and you just hang it from the top, there will be a length of the steel that no matter what you do, it will just break by its own weight because its cross-section area, its strength, and its density, they're all related. So there is a theoretical limit how long a bar you can hang or a wire you can hang from some point. Same is the case in compression. There is a limit on how much load you can, how tall a column can be just to support its own weight. After that, it will crush under its own weight. And you can easily calculate that based on FC prime or whatever you want to do. But there is a limit. But obviously, nobody needs a column that doesn't carry any load. You need a column that carries a load. So then column must carry, at least, 80, 70% or 100%, 200%, four times more load than its area. Then we talk about different materials and so on. So the weight of the self-weight or the weight of the simple gravity weight because of the gravity density itself will become a challenge. And then the solution is of course lightweight materials and also high strength materials. Weight on foundation is another challenge. The soil can only take so much. So if the soil is not capable, if the bedrock is very far, like Bangkok or other places, then there's only so much you can do. In fact, the 600-meter tall building that Dr. Karum did not present is being planned. One of the challenges, the foundation isn't strong enough. The soil just isn't there to take that building. Again, lightweight and high-strength materials could be an option. Axial shortening of columns is another issue that with height becomes significant. Creep, long-term differential shortening between the core and the columns because of the different level of axial stress and creep. So that line starts to become longer and longer until the floors will be inclined after 5 years because the axial shortening of the outer column will be much longer. So those kind of things start to become very significant issues, and they increase when the height of the tallness increases. Exponential increase in wind load. I will leave that, because Penning is going to talk about that, wind load and height parameters. But it's an exponential increase with height. So we need more aerodynamic forms, smart devices, and so on to tackle that. So these are the challenges that we get from the tallness. Challenges that we get from multi-use. We heard so much about multi-use, that buildings have to be multi-use for many architectural and living reasons. But they create difficulty for engineers and architects and planners because then you need to plan the building for different usage. And we have seen extreme problems because of the change of the use between top, middle, lower, and much lower portion of the building. Parking in a building becomes an issue. You need to park the cars, you need a certain width. So if that translates above, the plan above cannot be. And if there is a hall like this and there's a building on top of that, I'm sure there's a transfer mechanism somewhere. So every time the use changes, you get into trouble with the structural system, and that creates difficulties in especially electrical load resisting systems, ductility, and many other issues. So changing grid lines, offset columns, column transfer, different load, different performance criteria, even the performance criteria will change. Because for a hotel, it's different, office is different, residence is different. So within a building, you will have several performance criteria to satisfy because of the multi-use. Slenderness, we talked about slenderness a little bit. Slenderness is another major challenge, and architects and many people like the buildings to be slender. They are very, very inspiring for some reason. Dangerous looking buildings, but still safe, right? So, for me, I have this, every time I'm driving and I look at it, that seems too slender. I hope it's okay. So, in the back of mind, we always evaluate the building that are too slender, and I'm thinking, oh, did they check the drift of that building? And I'm driving, I shouldn't be doing that, but that's what happens. Drift is a concern that links to many things, because drift links to non-structural damage, to facade damage. So drift is one of the key criteria to control, and slenderness leads to larger drifts. And thanks to our elevator friends, if there are no cores, the drift is going to be the biggest problem we are going to have, because so far the drift is being controlled a lot by the core walls. And if you have smaller cores or no cores, then drift, I don't know how we will control the drift. We get larger natural periods, make the building flexible. You need damping devices. We looked at some devices in the morning, interesting application of dampers. Flexibility, we need to increase the stiffness somehow by adding components, by modifying systems. Overturning, buildings may be overturned. We need anchorage, we need column. A lot of buildings now, standard column buildings that we have evaluated, their columns become in tension. That's just not good to have a column in tension, because it really requires a lot of detailing on anchorages, on splicing, on many things. The column in pure tension is not a good thing. So if the columns become in tension, even with the effect of the gravity load, that means the building is really slender. High acceleration, the buildings we may experience high acceleration, so we will need, again, dampers of different kinds. So slenderness is one of the key challenges. Wearing plans, plan changes along the height. This is very fashionable. Now I will show you some examples later. And then if that happens because of the change in twisting building or just the plan is being changed for use, then we get into vertical load transfer irregularities, lateral force transfer problems, inclined vertical members. We have seen many of those challenges in our presentation from SY in the morning. They have shown in real buildings that these are real challenges that they are facing right away. So many buildings with inclined columns and with vertical and horizontal irregularities. We thought this is a problem of these short buildings, but in tall buildings, these are also coming up. And we have seen how they increase the cost, they increase the penalty in terms of the design parameters. So those challenges are very much real. Another challenge that we almost always face is floor to floor height, trying to minimize that because of several reasons. The client would like to build as many floors within a given height as possible, or they would like to reduce the height because the facade height can be reduced, the services can be reduced, elevator travel can be reduced, whatever, everything is related to height. So if by any means the total height can be reduced, people will like to do that. This table is just estimation, very rough calculation of what can happen by using different systems. If you use RC beams, for example, for a 200-meter tall building, you get 51 floors approximately. If you use rib slabs, you get 54 floors. If you use steel beams, you get 55 floors. If you use flat slab, you get 58 floors. So 6-7 floors can be added into the same height by changing the structural system. So obviously, that is something that will be interesting to study for the client point of view. They would like to see how can they put more floors into the same height, or reduce the height in other ways. So we can see that for 50 floors, we can get in height from 195 to 170 floor, 170 meters, 15-meter difference in height by changing the structural system. Form versus wind. These are two interesting examples that I found, which I think are very interesting, because we know that the wind profile exponentially changes. The wind pressure profile changes exponentially as we go high. So the building on the right is ideally tapered to opposite that effect. So almost the wind pressure can on the top is negligible because the area exposed to wind is very small. So the height is not having much premium in terms of the impact, in terms of the overturning moments and so on. And the base is wide where the wind pressure is low. But the other building is strange because at the top they decided to make it bigger where the wind pressure would be the highest. So obviously the wind overturning moments and forces in the two buildings would be very different even though they are of the same height. So that is another important thing that we have to see, that whether the wind design considerations, how they interact with the building form and design. And I mentioned about the twisting, turning towers trend, 3-4 T's. And this is just becoming more and more, and every day I see more buildings being designed which are twisting as they go up. Somebody did one building, and now very tall buildings are being done in this twisting form. Just one building just finished recently, and it's unbelievable to see how steep the twist is. And obviously, these twisting buildings are presenting with their own huge challenges because of the diagonal. These columns, they don't even have the columns anymore because columns can be inclined. You can't call it a column, the level of inclination that they have. And they're twisting and out of plane, and all kind of things are happening. The only thing keeping them in place is the core at this time. Don't worry. Like for example, this building just finished, and you can see how much twist in this building is. And even though we have slabs, we have no concept of the vertical columns outside. But actually, if you look at the structure, it's deceptively simple inside. Still the core is vertical, many columns on the edge are still going vertical, cantilever slabs are being done, so they have managed it well without actually making the structure any inclined columns. So deception is very interesting in building of this kind. Inside, if you look at the plans, they are able to create these forms without changing the structure much, except some large cantilevers and some few inclined members. Yeah. So lack of vertical outer members, the shell form concept. People are thinking that we should design the building as a shell, as the outer skin working as a shell, more like a tubular concept of the past or present. And then we have a lot of long cantilevers, and we can try many things. Coming back to the core again. So core is the core of the building. And somehow everybody is fighting for it. Starts with the elevators, the fire people, the mechanical and electrical people, the plumbing people, everybody wants a piece of the core. And structural engineers obviously rely on it for the structural strength. And I remember, especially with Boise, every time they send a building to us for performance-based design, we almost always find one thing common. Vertical moment capacity is fine from the code. Shear capacity is underestimated by the code, so we want them to increase the shear strength of the walls. So the wall thickness needs to be increased. But yes, thank you. So the wall thickness needs to be increased, and as soon as we touch the core, we get cries from everybody, because elevators, obviously, they're already designed to fit in there, and there's this set of elevators, not one. So where do you increase the thickness? There is no way to increase the thickness because they have fixed it for their elevator travel. And there are many elevators are side by side. So what do? You can't change the thickness, and the architect doesn't want to cut into the sellable space. So core wall estimation is one of the most critical design parameter that I will talk about tomorrow when we talk about the preliminary concept, preliminary design. That we need to make sure that we estimate the core sizes, wall thicknesses correctly. And like for example in Bangkok, let's say the building that I stay in is 40 stories. It shakes badly every time an earthquake happens 1,000 kilometers away, like First Melon said. In fact, last time it was very funny. I was sitting there a few months ago, and my son was sitting and working and watching TV, and suddenly I said, "Why am I so dizzy?" And I asked my son, he said, "Also, I'm feeling dizzy. Did we eat something wrong today? You're all feeling dizzy." And then we realized, no, it's not the food. It's the building that is swaying. And then we saw the chandelier. We are on the 37th floor. So we saw the chandelier moving. And then while it was happening, I called Mr. Pennant. He was driving somewhere. And I told him, my building is moving. He said, "What's the frequency?" And I told him, it's about 2 seconds. He said, "Yeah, it sounds about right." And he said, "I don't feel it because I'm driving." I said, "Yeah, but I'm in the building." So we are communicating while the earthquake is happening. And then we are thinking, where is it? I said, "It must be Myanmar." And sure enough, after 30 minutes or 15 minutes we checked, it was actually Myanmar. So that is how the buildings in Bangkok sway, because the core walls in my building are really small and the thickness is too small. If I'm a designer, I won't do it, but I live there. In Philippines, it won't work at all. So the core thickness 30 or 40 centimeter typical, or 30 centimeter in Bangkok typical, will be 60 or 70 millimeter in Philippines. So you can see right away the difference between the shear demand controlling the core and obviously the whole design. So the core is something that's very critical. It has ductility, it has a shear capacity, it controls the drift. Everything is actually core. Even if you put outriggers, core is still needed. Give me 5 minutes more. Okay, thank you. Buildings are designed around the core. If you look at several buildings, and this is actually a very interesting document I came across. And this is a thesis done in MIT by an architecture student. And he has looked at different buildings and tried to see what kind of primary system they're using. And he found that core is still the key in many of these small buildings. The spine is still there. So buildings are still designed around the core, both structurally and architecturally, very much, even the tallest ones. And if you look at the future buildings that are going to be completed by 2020, they are still primarily core-based with a few outriggers or mega columns and a combination of core and mega columns and something like that. So core is still critical in most of these buildings, not in all the ones that are completed, but also that are coming up for completion soon. So design of the core, sizing of the core, detailing of the core is everything in a tall building from the structural engineer's point of view. But unfortunately, the core is getting smaller. This is the layout plan of the Empire State Building. Look at the core size. It's more than half the building, because at that time the elevators were really slow and they need to use many of them, and that core was very big. Now it's not the case. The cores are getting really smaller. So we can see the changing size of the core and number of elevators as we are progressing, and that is causing structural engineers difficulty in terms of getting the right stiffness and ductility into the buildings, and other systems need to be added to help. So we are getting lack of stiffness, we are getting lack of flexural ductility, we are getting lack of shear resistance, and so on. And all of that because the cores are reducing, or the cores are, people are trying to minimize. Of course, high-strength concrete is being used to the limit in cores. China, they use composite cores. I was quite surprised. I was working on the development of the CSI call program, and then CSI people sent me a model in CSI call, and there's a shear wall model, and it was filled with steel sections inside. And I had not thought about steel sections, so many steel sections inside a core wall for the capacity calculation and moment curvature generation. And somehow the logic was not working well. So I thought, oh my God. So they're putting steel, a lot of steel sections inside the RC cores to solve the problem of the smaller core and smaller thickness with the high strength steel. Distributed core, theoretically speaking, could be a one answer. Rather than having single core, you distribute the core towards the middle and to the corners or the ends. Of course, this is only theoretical. Architects planning, otherwise it might not work at all. But if the core is distributed, then you can get about 5 times stiffer structure for the same core for the same building. But this is just theoretical, simple calculation. It doesn't mean it will work. But it just shows that distributed cores can be more effective than the central core system, as long as they are connected well with each other. And last slide on this core, one more. Mega columns. The alternate is that you combine the smaller cores with mega columns. Couple of columns, big columns, really big columns on the outer side, connected to the core through a series of outriggers, and that becomes the main structural system of the building. So the core is basically sort of stabilized and balanced by a series of mega columns, and all columns connect. And this is becoming a very common structural system for very tall buildings, and a few outriggers along the height. And one of the problems related to that is the spandrel depth in the core walls or in the coupled walls. And that is to me, we face it on daily basis. Our engineers, Ong and other people, we have a meeting every time at a project and say, what can we do with this? Because this portion that connects the two parts of the core wall or couples the wall becomes very critical. And it has two very opposing things to do. First of all, this spandrel needs to remain elastic, so to speak, for wind. And if you put a lot of reinforcement, then it attracts a lot of moment and fails in shear in earthquake. So now the problem is that if you put a lot of reinforcement for bending moment, you end up having a lot of shear demand for earthquake, and you cannot design it for shear, and you get into this strange place where you can't, they say between a rock and a hard place kind of thing. You can't do anything. Because one side is wind, one side is earthquake. And this spandrel, you cannot change the height because there's a door beneath that. You cannot change floor height. So there's not much, you cannot change the thickness, the core wall thickness won't be allowed. So you get into, then you put steel diagonals there, you try many things, and people have come up with special spandrels, and I think, Boise, you're using on some projects, right? Yeah, so these specialized, very, very like devices. So spandrels are becoming more like energy dissipation devices rather than members of the core wall. So this is another challenge that you will find in design of the core wall. I think I'll stop here. Thanks so much, and I'll continue again tomorrow before the presentation.